All right, everyone, here's another video that's going to revisit chapter 7.4, not only because I think it'll do you good in getting exposed a little bit more, but also to give you a real life example using something that I'm doing in my own life. And then we're going to move on to chapter 7.5, which is also something that I'm doing in my own life, and that is mortgages. Being able to do an annuity formula is great, but that's still math until you know how to apply it. So basically, calculating a present value of an annuity is something slightly different than just calculating a present value of a compound interest formula. Okay, and it's a slightly modified version of the annuity formula that you had before. It's not just algebra, so you may have to brush up on just either memorizing or setting to memory as best you can. And if you have a good understanding of present value of an annuity, you'll see how that also applies to your own retirement plan. So let's say you're going to be all bougie and hipster or whatever, and say mortgages aren't for you. You're doing that, live out of a suitcase and travel and rent everywhere you go kind of life. You're still going to retire someday, I'm assuming. Okay, so even if you may not be a home buyer sometime in your future, you will probably retire in your future. So please take a look at how this might apply to you. First and foremost, chapter 7.4. Quick story. When my baby girl was born, the week after she was born and all the craziness sort of settled down, my next main goal was to beeline it to the bank so I could set up something called an RESP for my baby. What is that? That is a registered education savings plan. Long story short, when my baby, who is now 1 year old, goes to from 0 and gets to 17 years old, that's some of you sometime next year, they might be planning to go to post-secondary education, right? And she was born in 2019. 17 years from now, that's going to be 2036. Oh, Lord of mercy, that's a long time. I'm going to be old. Okay, at 2036, I looked up the websites to see exactly how much that is going to be. And let me change my screen share to the cost of university and colleges. Hope you see that. In 2013, a 4-year program is going to be $125,000. The first year is going to be about 30,000, and due to inflation, a little bit, it's going to continue growing. So when she turns 17, I need to have $125,000 in my bank account. Good Lord, that's a lot of money. Safe to say, with my teacher paycheck, that may not happen. So what do? Well, I started a registered education savings plan. That's basically, this is one of the two things that I invested. So this is a product that TD Bank provides. And over the course, if you take a look down here, not that down, never mind. Let's see, year to year, how much does it cost? Average return. If you take a look at this line, it says that over the past 10 years, this particular mutual fund was able to give a 7.8% return per year. Okay, and if you take a look here, from 2009, 1 year it gave 30%, then it gave 9. It didn't do too well here, 9%, 12, 11. There was, I think, some kind of, I forget what happened to the world, but it went into the minuses, then plus, minus. 2019, I think it started a little poorly, and then 2020, it's going to go down again because of coronavirus, right? But anyways, this is what's happening. So I am going to check out what that would look like if it was, if I was to, calculate an annuity based on that as my interest rate. So let's start. How much am I putting in? What is my repeated payment? My repeated payment is basically $25 every single week. So what is my compounding period? I'm doing this 52 times a year. How many years will that happen? Well, it's going to be 17 years. Let's see, what else is there? What is my interest rate? Well, as you saw on the fact page that I showed you just now, it is going to be 7.8% on average every single year. What is my total amount going to be if I let that occur for 17 years? Let's take a look. Okay. Oh, please note, when you do a registered education savings plan, because you are sort of investing for the future of Canada, the government of Canada tries to help you out by putting money into it with you at a ratio of 1 to basically 20 cents. If you put $1 in, they'll put in 20 cents up to about $500 a year. I'm getting too much detail, but that gets too complicated. So let's pretend on my own strength, how much am I going to raise for my baby? My final amount is going to be $25 repeating every single time. 1 plus 0.078 divided by 52, of course, all to the power of 17 times 52 minus 1, all divided by 0.078 divided by 52. It's a bit long-winded, but let's see what I can do on my calculator. 0.078 divided by 52 added by 1, all to the power of 17 times 52. Okay, subtract by 1, divided by 0.078 divided by 52, multiplied by 25. That's what I believe it's going to turn out to be. Okay, and just in case I'm making any mistakes, I'll do it one more time. Plus 1 to the power of 17 times 52, subtracted by 1 times 25, divided by 0.078 divided by 52. Yeah, okay, so that is basically nothing compared to the $124,000 that I might need. But yeah, I do have something else set up with that as well. So hopefully that'll, you know, sort of soften the blow a little bit. But this is one of a few different investments that I'm making for the sake of my child's education. Might not seem like much compared to $125,000, but remember, I have some other stuff going on, so you could think about that times 2. At the same time, this is absolutely better than investing or saving my money and doing nothing with it. For example, if I'm doing $25 every single week times 52, and I do it just 17 times without any interest, and I just calculate it flat, that turns to $22,100. Okay, then 22,100. You see the difference? Huge difference, and this is why I'm doing it. Okay, so that is regular annuity. You'll see it everywhere, and you'll end up calculating this for your own sake as well. Okay, so I'm going to erase this and point you to a new lesson, and that is going to be chapter 7.5, Present Value of an Annuity. I'm going to introduce the formula for it because it's slightly different than what you've seen for regular annuity. I will also point you to the top right corner where there are not only chapter questions for you to try right here, but also we are at the end of our financial math unit. So there's a review section for you here too. Chapter 7.5, present value of an annuity, okay, is somewhat similar to our formula for before, but instead of A, it's PV. Instead of how much I have to put in, R represents how much we're going to be paid out. Okay, I'll make a better thing, better explanation later. The formula is very similar to the previous. However, Do you notice that the rate comes second? It's not the rate plus one, rate minus one. It's actually 1 minus the rate. And the exponent is 1 negative and times t. And all of that is to the power divided by r over n. Okay, slightly different. Try to compare that with the regular annuity formula. Okay, slightly different. So let me give you a bit of context of where this formula might be used by drawing a number line again and going through an explanation. Okay, let's deal with retirement. Sure. Doot, 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 dun, and dun, 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 dun. In retirement, let's assume that Mr. Kim is going to retire at the age of 65 years old, and he's going to live it up in a frugal way, of course, because I'm all responsible like that, until I'm the age of 95 years. Okay? But since I don't have a job, I'm going to be poor. I have no money coming. I have no paycheck. So what am I going to do now? Right? So this is from the age of 65 all the way to the age of 95. For 30 years, I'm going to ask the bank to give me some of my money in little bits at a time. My money. But if I give the bank a certain amount of money, and I'm asking the bank to give me a little bit at a time, just a little bit, just a couple of points, let's say, what happens to the rest that the bank holds on to? The bank will invest it. They make some money off of mine, off of the cash that I gave them, and they'll give me a little bit of that as a thank you. So think about it this way. A good way to describe it is this. If I give the bank a certain amount of money from now, let's say I'm like 30 years old, all the way to 65, for 35 years, I gave the bank money and they're going to invest until I have a pile of cash. Okay? So here's what happens. So at the age of 65, I have this pile of cash. I want the bank to give me, let's say, $3,000 this month so that I can live out the retirement of my dreams at the first month of 65. And then my second month, I want the bank to give me another 3,000. I want the bank to give me another 3,000. I want the bank to give me another 3,000 and another 3,000, another 3,000 every single month until I get to the very last month where I'm assuming that I'm going to sort of move on from the world after that, after that time. So 30 times 12 months per year, that's basically going to be at my 360th month, I want $3,000. And this is my 0th month from retirement. And this is how present value of an annuity is. If the bank in my first month gives me the first bag of money, look at all the other bags of money. The bank will take that and they will still earn interest on it. They will invest it and they will make money off of that, giving me a smaller bag of money. The next month, I'll say, hey, bank, give me my money. And so I take a bag of money from the bank. But the bank still has 1, 2, 3, 4, 5, 6, 7, 7 and a small 7.5 bags of money left. So they will still invest the rest of that and make another smaller bag of money, right? The next month, I take another bag of money, but the bank still has 6 plus 2 small bags. And so they'll make another small pot of money if investing it. So initially I had 1, 2, 3, 4, 5, 6, 7, 8, 9 bags of money. And you think that I can actually only go for 9 months before I run out of money. But that's not true. While I take one bag out at a time, I am continually making interest. So the amount of time it takes for me to run out of money is actually longer than 9 months. And that's what the present value annuity calculates for you. Here is where the math comes in. So that was sort of like the application. Here's what the math comes in. If I need $3,000 now, how much time did this $3,000 have to grow in interest? That's a trick question. The answer is none. But what about the next one? Let's pretend at a rate of, once again, let's pretend the rate is 12%. So it's 0.12 for the sake of example. If I need $3,000 a month from now, how much money do I need now for it to grow to 1 month and become 3,000? Well, it should be 2,900 and something, I'd imagine. Is there able to calculate that? There is. Take a look. Do you recognize this? Compound interest. If my final amount is going to be 3,000, what is the principal have to be? One month. Right? So this is basically P equals 1 plus R over N, and then NT, right? Time would be 1/12 of a month, and the compounding period is 12. So 12 times 1 over 12 is 1. That's where it comes from, right? So how do I get P all alone? How do I know what the principal value is? Well, I take this entire portion and I divide it to the other side. This becomes 3,000 divided by 1 plus 0.12 divided by 12 power 1. Another way I could write that is 3,000 multiplied by 0.12 divided by 12 to the power of -1, right? Because you know that if you have something, an exponent in the denominator, you can turn it into a -1 and place in the numerator. So to get to 3,000 after 1 month, I would need which turns into 3,000 divided by 1.01. I would need 22,970 and 30 cents right now. That's all I actually need. And 3,000, if I need $3,000 2 months from now, I can effectively say that 3,000, I don't actually need 3,000 because I have time. What I need divided by 1.01 to the power 2, I need 2,940 and 89 cents, right? So it's a lot less than 2,970, and it's definitely a lot less than 3,000. And the third month, I know I need $3,000 in 3 months, but that means I have 3 months of interest to gain. So what is that? 1.01 to the power of 3. I actually need a lot less. So can you imagine? I do this for 360 months. How much money do I actually need now for me to collect $3,000 in 30 years, in other words, 360 months? Well, that would be 3,000 divided by 1 plus 0.12 divided by 12 to the power of 359, right? To the power of 359. I only need $84. And in 30 years, it's going to grow to 3,000. Not a bad deal if you think about it. Okay. So here is the plan. All of these, and let me try to highlight it. 3,000 and a negative exponent of 1, a negative exponent of 2, a negative exponent of 3, a negative exponent of 4, 5, 6, 7, 8, 9, a negative exponent of 359. All of those added together, if we apply it in a geometric series, sort of, I guess, play around with the numbers, we will essentially get this formula. Okay, so let me rewrite the formula and try to describe what all of these letters stand for, and hopefully you'll be able to apply it in some example questions. Okay, the present value, which is how much you need now, so how much you need presently, is going to equal capital R, just like before, 1 minus 1 plus R over N to the power of negative NT divided by R over N. Okay, let's get some color in here. So R is not how much you're paying into it, obviously. This is how much you are getting out for retirement, right? Repeated amount that in this case that we're getting out. Okay, right. R and R, that's going to be the percent interest rate per annum, so every year. And just like before, we have N, N, and N. That represents the compounding period per year. So it could be 52, it could be 365, it could be 12, it could be 24, 26, so on and so forth. And lastly, my T, just like before, it is time in years. Okay? Yeah. Another interesting thing that you see this being used in is mortgages. Let me change the context. You want to buy a house, right? You want to buy a house that's, let's say it's going to cost you $500,000. Okay, that's how much you need now. But you're only able to pay, let's say, $2,000 right now. The next month, you were willing to give the bank $2,000. The next month, you're willing to give the bank $2,000. The next month, you're willing to give the bank $2,000. And basically, you're willing to give $2,000 every month until you pay that back. And the bank is like, sure, why not? However, let's be real here, okay? If you are paying me $2,000 next month, that is the same as you paying me a smaller amount now, because if you pay me that smaller amount, I could have invested it and made that extra little bit anyways. Let me give you an example to just get some numbers in there. Let's pretend the bank is willing to give you a 3% interest rate. Okay, so the question remains, if you gave me if the amount that is going to be paid is $2,000, how much did you give me now? Well, let's do it. P is going to be $2,000 divided by this exponent portion, and that's going to be, let's see, 2,000 divided by that. 1,995 and 1 cent. So basically they're like, yeah, if you give me $2,000 next month, well, it's like you gave me 1,995 and 1 cent, because I could have taken that money and turned it into $2,000 myself. I could have earned that extra $4.99 by myself. So you didn't give me that. So you still owe me that much. Here's another way you could think about it. You know how you had $500,000 to pay back in debt? After the first month, or on the spot, you subtract that much, right? So what amount do you owe the bank? This much. In the next month, you pay $2,000, but it's not that you owe $496,000 back. You actually owe $496 plus an extra $4.99, because remember, you actually didn't pay that $4.99 back. You only paid back $1,995 and 1 cent. A bit of a cheese ball, isn't it? Well, when it comes to mortgages, the formula is exactly the same, but how you describe each variable might become slightly different. Specifically, what's different? Only one thing, or two things. Okay, your current debt. Okay, this is how much you need to pay the bank back in the very beginning. So present value, the present value of your debt. The rate is the same that you are charged. The amount of times, it's the same amount of time. Instead of being paid out by retirement, you're paying the bank back. There's a compound period. The repeated amount isn't how much you're getting paid by the bank. The repeated amount is how much you're paying the bank. Hope that sinks in. Without me being in front of you, it's a little hard to explain, but let's try some examples in hopes that you can see some of these formulas in action and get a better sense of, or better understanding of it. Okay? The first example that I'm going to do is example 1. So go to page 458 in the textbook. Example 1 says this: Josh is putting his summer earnings into an annuity from which he can draw living expenses while he's at university. You get it? He's making a big bundle of cash so that he could take small pieces out of it while he's in university. Not all at once, but just small pieces. How do I know it's going to be present value of an annuity? Well, if I take a small portion out from this bit, if I take a small portion out, right, the remaining part of this dollar bag is going to continue to grow. It's going to grow. And if I take another portion out, the remaining parts of this bag is still going to grow a little bit. If I take another portion out, the remaining portions of the bag will still grow a little bit and a little bit, so on and so forth. Okay? So reading the question and understanding the context is going to be really important for you to decide whether it's just a regular annuity, if it's a present value annuity, so on and so forth. Okay? Let's continue. He will need to withdraw $900 per month for 8 months. So I want to be able to take out $900 per month. That automatically means my compounding period is going to be 12. How much is the time? Not 1 year. It's 2/3 of a year. It's 8 months out of 12. Interest is earned at a rate of 6%. It's compounded monthly. Well, you already knew that. So, draw a timeline? No, thank you. How much does Josh need to invest right now for this to happen, for him to be able to take out $900 a month? Well, part B, what is my present value if my repeated payout is 900? If my growth is 0.06, if my compounding is 12, plugging that into the calculator, 0.06 divided by 12 plus 1, all of that is the power of a -8. 1 is subtracted by that number, multiplied by 9,000, divided by 0.06. I need $7,040.66. It might still seem like a lot of money, but think about it. Compare that to how much you'd have to save up if you didn't use the bank's interest system. That's $900 per month for 8 months. Quick math, that is $7,200. So you're earning about $160 in interest during those 8 months. It's not bad at all. Let's continue. Example 2 on page 459. Fiona's life savings total $300,000 when she decides to retire. Ooh, that means my present value is $30,000. That's how much I have right now, or she has right now. She plans an annuity that will pay her quarterly for the next 30 years. If her account earns 5.2% per annum, compounded quarterly, which we know, how much can Fiona withdraw each quarter? How much can I withdraw each quarter? Well, plugging it into the formula, my PV this time is 300,000. My R is there. 1 plus 0.052 divided by quarterly, negative quarterly times 30. So this time around, because I'm going to have to do a little bit of algebra, I'm going to actually solve that bracket portion first. Divided by 4 plus 1 to the power of negative 120. 1 minus the answer divided by 0.05 divided by 4. Oops. 60.595444488. That means R is $300,000 divided by 60.5954 or something, which gives me this much every month. Sorry, every 4 months. Okay, and this is not from the government. This is my own money that's coming out. But because it's coming out in pieces, I'm going to actually be able to take out a lot more than $300,000. Think about it. If I'm able to do this every 4 times a year for 30 years, how much money am I actually able to say is mine? $594,000, 104.40. So although I have although she has $300,000 right now, because she's letting the bank invest it for the 30 years while she's only taking a little bit at a time, the bank is growing that money incredibly high, so that by the time she runs out of her funds, she actually took out this much from the bank. Pretty crazy, huh? That is why you actually don't need that much money. So you might have heard of the number 401k. And in business, that's basically how much they think you need. That's the present value you need when you retire to be able to withdraw a comfortable amount of money every month and still be able to last you until you sort of, pass away. Okay. That brings us to the end of our examples, but I have a feeling there's going to be a handful of people who want to ask questions anyways. Please try these, as I said before, page 461, numbers 1, 2, 3, 7, and 10. I believe that was what I assigned. If not, please correct me, but I'm pretty sure. Give me a second. Yeah, 1, 2, 3, 7, and 10. And then go to the entire chapter review starting in page 464. Just do all of them. They're going to help you out. Please, by all means, send me an email or ask me a question on how to use this formula and better understand the context of questions. As I said from the very beginning of this chapter, compound interest, financial math, even if you don't understand anything or you forget everything from math class, this is something that essentially everyone is going to have to do if they want to be financially responsible of their future, right? Being able to retire, being able to plan for your own retirement, be able to figure out how much you need per month to have a comfortable retirement. All of these things are important. And of course, finding an investment that gives you a really, really good growth rate, right? All of these things are things that you're going to have to consider as you continue growing older. So do yourself a favor. You're only 16, not going on 17. Learn this financial math. The 20-something-year-old you will thank you for it. Do your best. Ask me questions. Don't stop. And yeah, take care of yourself. See you in the next one.